The next presentation is myself. I'm Babak. I work with Dr. Hashemi here at I2S, and my research is on edge computing and quality of service, quality of experience. What's this one? And my research is on quality of experience maximization, and especially for virtual reality applications. And I use machine learning methods, specifically reinforcement learning methods, to solve optimization problems for virtual reality glasses and streaming applications. Today, my talk, this is the outline of my talk. I will go over the motivation for my research, and then I'll delve into details of my presentation and my work system model and the problem that we are addressing and the solution that we are providing. And at the end, I'll provide some preliminary results. So every day, at the edge of the network, we see more and more computationally intensive application and bandwidth-hungry applications that require a lot of bandwidth and applications that require a lot of computation. And those applications are either on our phones or on our computers, which have limited computational power compared to servers in the cloud. Some of these applications I have listed here: location-based augmented reality, virtual reality, online 3D gaming. You can see that all of these require huge amount of computation and huge amount of bandwidth. In our case, we are considering virtual reality applications. And according to the newest standards that we have, a 12K high quality spatiotemporal resolution is required for a good quality of experience for users. 100 frame per second rate is required compared to 60 frame per second that we had previously. And all of these introduce more loads into the network, into the computers and our devices at the edge of the network. But these are not the only challenges. We can divide the challenges that we have in these sort of applications into 3 different categories. These categories are computational constraint. We have limited computational resources at the edge of the network on our devices, on the VR glasses. Sometimes you use your phone and connect it to some sort of goggle to play some sort of virtual 360-degree video. Our phones are not designed to stream or render those type of videos. So they have limited computational resources. Network constraints. We have limited bandwidth for a 12K video. Right now, the highest quality you can play on YouTube is 4K, and even sometimes here I have, with the great internet that we have in Naples, I have problem playing a 4K video on my computer. So how can we play a 12K video on a goggle? And 360-degree videos, to be honest, are huge. One 360 video for, like, I would say 30 seconds, it's like 12 gig, 13 gigs. So that's a huge amount of data, huge amount of computation, which requires a huge amount of bandwidth. And there are a lot of investigations out there and a lot of solutions out there to address each of these challenges separately. For example, one of the things that is out there is predictive streaming and caching. And especially with goggles, virtual reality goggles, you have a 360-degree video, but you are only looking at a certain angle. You're only looking at a viewport. You have a viewport that you're looking at, and you're only streaming that to the user. So what people suggested is that let's predict where the user is going to look at in the next couple of seconds, and then stream it in advance and see. And in this way, we can save some bandwidth, save some computation if necessary, and provide a better quality of experience for the users. Another thing that it's more on the hardware side is that people try to develop VR headsets that can support dual connectivity. What do we mean by dual connectivity? It means that they can, at the same time, they can use, the VR headset can use millimeter wave technology, wireless technology, or Wi-Fi. And they can connect using both of these to a server that they are streaming from. Another set of solutions they have considered edge computing servers, where you locate a computational resource at the edge of the network, and that all of the VR headsets are connected to that computational server or edge computing server, and they offload their tasks, their rendering, their computation to that server for more computational power. Another one that we see every day, for example, when we are playing a 2D video on YouTube or somewhere else, is adaptive bitrate streaming. And it seems a more reasonable and more advanced method, and it tries to match up with your throughput, a network throughput, network bandwidth, and improve your quality of experience. But for VR streamings, we need more than this, because we have a limited computation. And so what we decide here is to combine all these three aspects: edge computing, adaptive bitrate streaming, and then use of millimeter wave networks to improve the quality of experience for the users. And here is the model that we are considering. We consider a VR arena where we have multiple VR users. They are all streaming different type of videos from a edge computing server, where we call it edge computing unit, and all of the videos are stored in this edge computing unit and will be transferred to the VR headset through a millimeter wave wireless network. And the way that we store these videos in the server is that each video is divided into different chunks, and with a fixed duration of time, fixed time duration. Every chunk works like 1 second, 2 seconds. And then we have multiple layers of, we call them enhancement layers or immersion fidelity, where as we increase the number of layers in the video, in the frame, the quality of the video increases, the bit rate of the video increases. And what we do is that we always stream the base layer for the whole panoramic video, but the place that the user is looking at, the viewport, we only stream both the base layer and the enhancement layer, as we call it. So here you see that for that viewport specific, we need to adapt the rate. We need to have some sort of rate adaptation algorithm to increase the quality of experience, to balance the trade-offs that exist, and to kind of respond to the user's demand based on the throughput of the network. And okay, so we will combine these two frames, the base layer, base panoramic layer, with a enhanced viewport-specific enhanced layer, put them all together, and then stream it to the user, to be buffered to the user at the VR headset. And then, but prior to buffering, we need to do a few things. VR 360-degree videos need to be decoded first and then rendered in order for the users to be able to play them on their VR headset. And after that, we need to transmit them. But one thing here is that decoding or rendering this computation, as I mentioned, is very heavy, and it can happen, it can take place either at the edge computing unit or at the headset. And there are some benefits to each of them. For example, if we do the computation at the ECU, edge computing unit, it's way faster. We will have a way smaller decoding time. We will have a way smaller rendering time, but it almost triples the size of the packets we are sending over the network. So that introduced like a large delay in transmission. And so that being said, what we did was we modeled the buffer occupancy of each VR headset, and then using that, we can define the quality of experience. If I go back to this one, you can see that buffer level stays at one level. As soon as we are at this point, we are requesting for a new chunk of video, and as soon as we are requesting, the preparation starts. And if we don't have enough, if the preparation time is larger than the amount of video that we have left in the buffer, we hit 0, and we start rebuffer, which is very unsatisfying for a user. So that's one of the major things in quality of experience. We want to minimize this rebuffering time. We want to minimize this red area in this plot. But that's not the only thing. We have other stuff as well. Another important thing is video quality. You can see here we have 3 different qualities: Full HD, 4K, and 8K. And you can clearly see the difference between this Full HD. I'm not sure how clear is it out there, but this one, Full HD, is a little bit blurry. But this one, we all prefer the 8K, right? But it introduces more computation and requires more bandwidth. Another thing is quality variation. When we are playing a video, we don't want to switch back and forth all the time between different qualities. We don't want to see 10 frames with Full HD and 10 frames with 8K. We prefer to stay on the same quality throughout the whole process. And we defined all these 3 factors and combined them this way. And then we define our multi-user quality of experience maximization, where we are maximizing the vector of the quality of experience in this case. And there are 2 very important decision variables in this optimization problem. One is the computation distribution, in which decides where the computation takes place, where the decoding and rendering take place, either at the ECU or headset. And the other one is the rate adaptation. How many number of enhancement layers we want to transfer to the user for a good quality of experience. But solving this optimization problem is not without a challenge. We have definitely many challenges. It's a vector optimization, it's a multi-objective optimization. So we need to play around and convert that objective function to something that we can solve. And the way we did it was basically taking the average of that vector and also taking this variance of that vector and maximizing the average while minimizing the standard variance or a standard deviation that is multiplied by a coefficient beta. But it doesn't finish here. We have other challenges as well. We have interdependent action space. What do I mean by interdependent action space? That computation distribution influences the maximum achievable rate. If I decide to do the decoding or rendering at the headset, it limits the number of enhancement layers that I can send to the VR headset, because the computational resources at the VR headset are limited. And it's opposite case also is true as well. And maximum achievable rate sometimes influences the computation distribution. And we also have heterogeneous users. Some of the users may play a very, I would say, lightweight video, and they wouldn't need ECU. So we need to be able to recognize those users to not waste the ECU's computational power on those users. And the network condition is also time varying and dynamic, and it's always changing. We designed this framework, Deep VR framework, where we are using the state-of-the-art Deep RL method, and we extended it to a multi-user case, and where we have these this information for each of the users, playback statistics and video information for all of the users, and these information go through two different networks. One is an actor network on the top, which gives out two actions: rate allocation probabilities and computation distribution probabilities, and also an auxiliary value which estimates the value. This value is basically the quality of experience for each of the users. And we have another critic value, critic network that does the same for the value and estimates the quality of experience. We trained this network using a well-known training algorithm for a state-of-the-art deep RL training algorithm called PPG, and it has a two-phase training process where in the first phase we train our policy, and then we have another auxiliary phase where we work on all the experiences that we have collected by interacting with the environment that we have. And during that phase, we do behavioral cloning. We try to mimic our past behaviors. And we train this agent on a simulated environment, but this simulated environment uses all real-world information and real-world data. One of the data sets that we have used, you can see one of the pictures I have here is a video captured it's called the runner video. It's a video of someone running in a field, and it's a 360 video. We have the information for 15 different videos, and we use those in the simulation. And we also have a data set of network traces collected from both Verizon and T-Mobile in 2 different cities. We use those data sets, these 2 data sets, and developed a simulation environment to train our network. And as you can see here in this 2 figures, the network could be very unstable sometimes and can fluctuate a lot. And our agent needs to adapt to this. We trained our agent on this environment with 6 users, 6 VR headsets, and we saw that our joint rate adaptation and computation distribution performs way better when we only use the computation distribution algorithm at the maximum rate, or we only do rate adaptation and leave everything else to ECU. So it seems like there is a trade-off between whether we want to upload, whether we want to use the edge computing server or not, how many enhancement layers we want to send to the users, and a few other trade-offs. If we look at more detailed quality of experience stats in these figures here, in this one, I'm reporting the average quality variation throughout 100 different episodes, trials, average bit rate, average stall time or rebuffering time, and that last one is the rework when we are testing it. And we see that in this one, the rebuffering time that our agent, our model provides is the minimum. It's not the minimum, but it's the lowest value. And we also provide a lower bit rate, which means that we have a more efficient bandwidth allocation for the users. In summary, we observed that a lot of computationally intensive and bandwidth hungry applications are emerging at the edge of the network, and there isn't enough. And with the new requirements, there's a need for new investigation in this area, especially quality of experience maximization for virtual reality glasses. And we developed this problem. It wasn't easy to solve it, but we proposed a joint rate adaptation and a computation distribution algorithm to solve it. And some of the initial results that we have shows big promise. And yes, that's all I have. These are some of the references that I have used the most. And thank you. If you have any question, I'll go for it. Yes.
How do you set your hyperparameter like beta, gamma, and nu in your
So that's a great question. So in this simulation, right now, beta is 0 because I want to have it without beta first and then see how it performs, how fair it is for the users, and then increase the beta and see how it will change the fairness in the system. So right now, I can say it's 0, but I'll definitely have an investigation of that, how it affects the performance and fairness among users.
So the reinforcement learning model, is it running on the edge computing? Or
Yes.
so how you can figure out if buffering is happening at the user end?
How can we figure out if the buffering happens at the
VR headset? Because that is one of the issues, right? To the reinforcement learning that is suffering and happening or.
I see what you mean. You mean the current buffer level here? This information?
Sorry, I think I mean that the user experience thing. If the user is observing a lag in the screening process, how the reinforcement learning will figure that out?
Oh,
This information provided to the ECU?
yes, it is provided, but with a delay. So we always have that delayed rebar in the reinforcement learning. And that's the whole nature of reinforcement learning, that can learn a policy to maximize a delayed rebar. We may receive this rebar after 10 seconds, we may receive it after 1 second. And in this case, after we stream each video chunk, we receive the rebar immediately in 1 second, I can say, with one chunk of delay, I would say. Any other questions? Thank you all. We will have a break, and then Tim is here. Tim will start his presentation for us. He is our keynote speaker today, and we'll have him maybe 20 minutes? 20 minutes or 30 minutes? Yeah. Okay, we'll see you back at 11. Thank you all.
Yeah, I had a question about the state.
Yes.
Is that available online?
Yes. Yeah.
Could you send me a link?
Yeah, I'll.
Because I use examples in my networking class, and that looks like a really good new one.
Yeah.
Yeah. I couldn't copy down your full testing. You just email me.
Sure. I have 2 other references as well.
Okay.
2 other network traces as well.
Great.
I'll send all 3 of them.
Thank you. I appreciate it.